Today we'll be learning about eddy currents and its applications. Let's first revise some concepts that will help us understand eddy currents better. First, look at this coil. When I move this magnet forward and into the coil, a north pole is created here. As I move the magnet away, a south pole is created here. Now let's take a second experiment. Here, a bar magnet is dangled from a stable support above. In the first case, there is just the magnet, while in the second case, there is a conducting slab near the dangling bar magnet. As we give an amplitude theta to the magnet, we observe that the magnet in case 2 comes to a state of rest faster than the magnet in case 1. That must mean there is some sort of opposing force that complements the air drag. This is in accordance with Lenz's law, which states that an induced electric current flows in a direction such that the current opposes the change that is induced in it. In other words, any increment in flux is opposed and decreased, and vice versa. Coming back to eddy currents, have you ever seen the ripples created when you drop a stone in water? These ripples are called eddies, and this is where the term eddy currents actually originated. So now, let's take a conducting slab and a bar magnet. Place the bar magnet perpendicular with respect to the orientation of the conducting slab. If we look at the setup from the top, it will look something like this. Now, as we move the north pole of the magnet closer to the slab, from the right-hand thumb rule, electric field generated should be in the clockwise direction. But as we have learned before, in accordance with Lenz's law, the current induced should oppose the current generated. Hence, the current induced will be in the anti-clockwise direction, and it will be in the form of concentric rings. This leads us to the very definition of eddy currents, which states that eddy currents are a type of circulating currents which are produced because of the moving conductor in an external magnetic field or a stationary conductor in a varying magnetic field. That is, if I were to move the conductor while keeping the magnet stationary, the results obtained would be quite the same. In other words, eddy currents entail the flow of electrons in such a way that increment or decrement in flux is opposed.
Another prominent application of eddy currents is the speedometer. We will be going through the speedometer in 3 topics: its location, its construction, and its working. Location-wise, the speedometer cable is directly linked to the output shaft of the gearbox, which is bolted to the rear of the vehicle's engine. The speedometer cable will rotate at the same speed as that of the output shaft. Coming to the main speedometer arrangement, the speedometer cable we talked about earlier is connected to a magnet. A speed cup is directly present above the magnet with no physical contact between the two components. An indicator rod is further connected to the speed cup, to which a hairspring is attached. Finally, the indicator housing, which is the panel you see behind the steering wheel, is connected to the end of the indicator rod. Due to the help of the rotating outer shaft in the gearbox, the speedometer cable is also caused to rotate, setting the connected magnet in motion. The magnet now begins to attract the metallic material present in the field cup due to the production of a magnetic field. The speed cup deflects as a result of this, further rotating the attached indicator rod and causing the hairspring to deflect. Finally, this causes the needle on the housing to move, hence showing the speed of the vehicle in accordance with the produced eddy currents in the drum.
Damping plays an important role in controlling the motion of an object. It is an effect which tends to reduce the velocity of a moving object. A number of damping techniques are used in various moving, oscillating, and rotating systems. These techniques include conventional friction damping, air friction damping, fluid friction damping, and electromagnetic damping. Electromagnetic damping is one of the most interesting damping techniques, which uses electromagnetically induced currents to slow down the motion of a moving object without any physical contact with the moving object. A type of damping in which an electromagnetically induced current is used to control or slow down the motion of an object without any physical interaction is known as electromagnetic damping. As a conductive surface moving past a stationary magnet develops eddy currents induced in it by the magnetic field. By Lenz's law, the circulating currents create their own magnetic field that opposes the field of the magnet. Thus, the moving conductor experiences a drag force from the magnet that opposes its motion, proportional to its velocity. Also, when eddy currents are produced in the moving object, heat is produced and hence, there is a release of thermal energy from the object. Due to decrease in energy, the kinetic energy of the object also decreases, so it starts slowing down.
Applications of electromagnetic damping. Electromagnetic damping is used in train and roller coaster brakes. In this case, eddy currents are produced by electromagnets attached to the brakes, which cause the train or roller coaster to slow down significantly. However, since the drag force provided by the eddy currents decreases with speed, it becomes too weak to completely stop the train or the roller coaster. So, to bring it to a complete stop, we use frictional brakes or even strong permanent magnets like neodymium magnets. The main advantage of using this type of braking system is that since there is no physical contact, wear and tear does not take place. Hence, there is no need to replace the brakes every few months. Another example to explain electromagnetic damping better is to take the example of a compound pendulum, which also exhibits damping in its frequency. It slows down due to the effect of the field of the earth when it's oscillating. The damping coefficient of any compound pendulum can be calculated using complex formulas, which we derive in the end to be gamma is equal to 2 into moment of inertia by tau into L square, where tau is the time period and L is the length of the string from where it's hung.
Greetings to all. In this presentation, my classmate Richik Datta and I, Chavi Gupta, will be giving an overview on the working of an induction furnace, which is an electrical furnace which follows a non-contact form of heating and is a cleaner method of melting metals to form alloys using electric current.
Let's talk about the construction of the induction furnace. The current-carrying copper coil is placed around or inside the crucible, which holds the metal which has to be melted. The crucible is divided into two different parts, with the lower section holding the melt in its purest form, which is the molten metal, while the higher section is used to remove the slag, the contaminants that rise to the surface of the melt. The two types of induction furnaces are as follows. Number 1. Coreless induction furnaces. The coil is outside the melting crucible. Number 2. Slot induction furnaces. The coil is inside the crucible where molten metal flows. The two ends of the current-carrying copper coil are connected to a high-frequency AC source.
The working principle of an induction furnace is induction heating, which is the process of heating an electrically conducting object, usually metals, by electromagnetic induction, which leads to the formation of eddy currents and produces heat by Joule heating. In electromagnetic induction, conductive material is placed in a variable magnetic field and eddy currents are generated at the site. The eddy currents flowing through the resistance of the material cause heat to be generated by the Joule heating effect, in which heat is given by the product of the square of current, resistance, and time.
Let's talk about the working of induction furnace. The copper coil which is surrounding or is inside the crucible is connected with AC voltage source with high frequency. The reversing current creates a rapidly reversing magnetic field that penetrates the metal, which has to be melted. Because of the constantly changing magnetic field experienced by the metal, the magnetic flux on it also rapidly changes. Now, according to Faraday's law of electromagnetic induction, change in flux gives rise to EMF, which leads to the rise of eddy currents. Now, how does this rise of EMF give rise to eddy currents? Because of the EMF generated, the electrons start moving inside the metal in a few definite paths. This is essentially the eddy currents. Because of these eddy currents flowing through the metal, which has resistance, the metal heats up in a phenomenon known as Joule's heating effect. As explained earlier, heat produced per second by current flowing in a conductor is proportional to the square of the current flowing through it and the resistance of the conductor. The copper wire is prevented from being too hot and melting using electromagnetic shielding and by cold water flowing in coils around the crucible, which leaves as hot water, is cooled again in a cooling tower and is recycled. In the end, because of the heat generated in the metal, the same metal melts and we get very pure molten metal, devoid of any impurities.
The advantages of an induction furnace are as follows. First, non-contact. Due to the non-contact form of heating, in which heat is transferred via electromagnetic waves, the inductor itself does not get hot, therefore leading to no product contamination, as opposed to combustion in traditional heating furnaces, which leads to loss of valuable alloying elements. Second, temperature control is done by controlling supply frequency. Changing operating frequency depends on the material to be melted. And third, it is energy efficient and non-polluting, as no combustion takes place, while other melting processes cause emission of dust and pollutants.
So, we have seen the advantages of induction furnace. What are the disadvantages? Firstly, it is very costly and the equipment is capital intensive. A person starting out on a venture probably won't be able to afford an induction furnace. Secondly, it has no refining capacity. If the original piece of solid metal is impure with substances like sulfur and phosphorus, the induction furnace does not have any method to purify the impure metal.
Eddy current breaks. Now what are eddy currents? Eddy currents are loops of electrical current induced within conductors by a changing magnetic field in the conductor according to the Faraday's law of induction. Eddy currents flow in closed loops within the conductor in planes perpendicular to the magnetic field. So basically the conductor generates a magnetic field and the magnetic field generates an eddy current. This happens due to the change in flux. Change in flux always induces a magnetic field. So how do eddy current breaks work? Electromagnets produce primary field from supplied current, which in turn produces eddy current. Eddy current, being an electric current, in turn produces secondary field which opposes the primary field. This secondary field opposing the primary field has a tendency to reduce the velocity since it is opposing the field, that is in the opposite direction to the primary field. So hence it applies a force in the opposite direction. So why are eddy current brakes useful? The main reason they are useful is because they are non-contact brakes. So throughout the working of eddy current brakes, there is no contact between any of the braking system and the wheels. So this way wear and tear due to friction and a lot of maintenance issues are avoided.